Let us next see this example. Here we have the ring of integers as our ring A, and in it we have this principal ideal generated by some integer m, which actually we are considering to be greater than 1. It's a positive integer and it's greater than 1. And the distinct prime divisors of this m are these pi's, p1, p2, like that up to pr. Then we have to prove that this is the claim that the radical of I is the principal ideal generated by the product of these pi's, and which is also equal to the intersection of these principal ideals generated by the individual pi's. I am leaving this second equality to you to prove. It is very straightforward. I don't think you will find absolutely any difficulty proving this one. So we are now going to prove the first one. So let's do it. Actually, this first one is also very easy. It's not difficult at all. So we are obviously going to show that each of these two sets is a subset of the other. Let us first show that the radical is a subset of this ideal. So we take any element x in R of I, then by the definition of R of I, some power of x will belong to I, where the exponent is a positive integer. Now what is I? I is the principal ideal generated by m. So every element in I is a multiple of m by some integer. So this x to the power n is also some k times m for some integer k. But m itself has these pi's as its distinct prime divisors. So each pi divides m, and in fact their product also divides m. And that is why m itself is of this form, some integer l times the product of these pi's. So now you use this information here and have x to the power n as kl times the product of the pi's. And from this, what do you see? You see that because each pi divides the right hand side, so each pi also divides x to the power n. For each such index I, pi divides x to the power n. But now you use the fact that pi is a prime. So if a prime divides the product of some integer, then it has to divide at least one of them. This is a basic fact from number theory. But it's a product of a number of x's only. So that is why pi has to divide x. And then each pi divides x, and the pi's are distinct primes, and that's why they are pairwise relatively prime. So their product also divides x, and that way x belongs to, now this part may be a little confusing notationally. Let me not use the round brackets here, because round brackets are denoting principal ideal. So you do understand that this notation means that the product of the pi's divides x. But then that just simply means that x is an integer multiple of this product, or in other words, that x belongs to this principal ideal. So that way any element here is also here. So this is the subset of this. And then we will go for the reverse inclusion. So we write that conclusion here. So because of those previous things, R of I is a subset of this principal ideal. And conversely, we take any element y in this principal ideal. Then y would be some integer multiple of this product, say q times this, or some integer, I forgot to write that, q belongs to z, but you understand. Now suppose this is the prime factorization of m. So far we have only been working with the fact that the pi's are the distinct prime divisors of m, but we actually did not really see or care what m really is in terms of these pi's. So let that be this, where each exponent qi is a positive integer. Now next what we do, we consider the sum of these exponents, and we are calling it s. And then what we do, we take the power of y where the exponent is s. Note that just like the qy's, the individual qy's, s of course itself is also a positive integer. So taking the s power of y means in place of y you are going to write this thing, and then s comes over each factor. Alright. Now we are going to extract m from here. What is m? M is this. So if we just simply write m without thinking of anything, then we have to make the necessary adjustment. So m contains these prime powers, p1 to the power q1 for example. So you have to also divide by p1 to the power q1. That gets adjusted with this power of p1, p1 to the power s, like this, p1 to the power s minus q1. Okay, so there is no problem in doing that, and you do that with the other factors as well. But next comes the question of whether these powers are themselves integers. If the exponent is negative, then it's not an integer, but the exponent is not negative. Why? Because s is greater than or equal to each qy. The qy's themselves are positive, and s is at least as large as each one of them. That is why each of these exponents that you see, s minus qy, is a non-negative integer. So this entire thing is an integer, and q to the power s of course is also an integer. So you are looking at an integer multiple of m. But m generates the principal ideal I, so that way y to the power s belongs to I, where s is a positive integer. But then by the definition of the radical of I, y belongs to the radical of I. So anything that you choose from here, y for example, is also in the radical of I. So the reverse containment is also true, from which you get equality. Let's write those things. So we have the reverse inclusion and we get our equality. And next we are going to see one proposition, again involving radicals. So next we have this proposition 116. It states that if I and j are two ideals in a ring A, I forgot to write that. So you have A here such that their radicals are coprime, then I and j themselves are also coprime. So let's see the proof. The proof immediately takes the help of this exercise, exercise 113, and it's part 5. By that we have this identity, that the radical of I plus j is equal to the radical of the sum of the radicals of I and j. Now it is given that the radicals of I and j are coprime. So this sum is the entire ring, that is the principal ideal generated by the identity element, whose radical turns out to be the ring itself. Let's see how. This is something very easy, but still let us see the details. So we first notice that the radical of any ideal is of course a subset of the ring. In particular, the radical of the entire ring itself is also a subset of the ring. So we have one containment here. Now let us take any x in this principal ideal, which is actually just the ring. In fact, that's why I have written in the next line, this just means that x is an element of the ring. A, we are writing A here that we previously forgot to write. But then the first power of A, x to the power 1, is x itself. First power of x, sorry, I said A. The first power of x is x itself, which is already in the ring and which is already in this principal ideal, which is the ring. So by the definition of R of 1, x will belong to R of 1. So that way, any element here is also in the radical. So you have the reverse inclusion as well, and that's why you have equality. It's almost trivial, but sometimes these trivial things may confuse us endlessly if we are not careful. Okay, I don't consider it a part of the proof in the sense that there is no need to write these things and show in the proof. But that does not mean that you just simply ignore it without knowing. You should ignore it in the sense that there is no need to write these things, but in your mind you know what you are doing when you are skipping things like this. Alright, so now next, what do we get from this? Alright, so in this last part of the proof, we first note that just like we have all the elements in the ring, in particular the identity element is also in the ring, which however we have found is the radical of I plus j. So the identity element belongs to R of I plus j, but then by the definition of radical, some integral power of one identity element has to belong to I plus j for some positive integer exponent n. But this is just 1 because it's identity, and that's how 1 belongs to I plus j. But we already know that I plus j is an ideal, and whenever an ideal in a ring contains the ring's identity element, it has to be equal to the entire ring. So that way I plus j is also equal to 1. But that just means that I and j are coprime, just like Ri and Rj are coprime. So that's the proof. And this ends our discussion on radicals for now. After that, we have extensions and contractions of ideals, which is the next topic. And once that is over, this chapter will be over. So we will start that next week. So see you next week with those things. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.